Okay, so in the earlier lecture, I talked about isotropy of space, and that leads to the law of conservation of angular momentum. Today, I'm going to talk about homogeneity of time, and this basically leads to the conservation of energy. Law of conservation of energy. It is the consequence of this. So let us try to prove it, that how homogeneity of time leads to the law of conservation of energy. Yeah. So first of all, let us understand what is the meaning of homogeneity of time. Homogeneity of time. Homogeneity of time means that any experiment or any physical law remains same in every time. Every time means it is independent of, that is, it is independent of present, past, or future. Means if some law is valid today, then it is also valid 100 years ago, and it is valid also 100 or more years ago, right? So now consider two interacting particles. So we are having two interacting particles, and yeah, so say it is x-axis, it is y-axis, and say it is z-axis. We are having two particles, one at x1 and another particle is at x2. This is first particle and this is second particle. So the potential energy between these two particles is given by u, and u is basically function of x1 and x2. But according to homogeneity of time, according to homogeneity of time, u should not be a implicit or explicit function of time. So what does it mean? That means mathematically that curly u by curly t is equal to 0. That's the meaning of time. This shows that u is independent of time, potential energy. So now we will try to prove that how this leads to the what we call it leads to the law of conservation of energy. So let us now consider u is basically a function of x1, x2, and let us assume that it is also function of time. So let us take its differential. If I take a differential of this, then it means that partial derivative of with respect to x1 and dx1 plus curly u over curly x2 dx2 plus curly u by curly t, and it is dt. So if I try to find a du upon dt, then this can be expressed curly u over curly x1 dx1 plus curly u over curly x2 dx2 plus curly u by curly t, because dt upon dt is 1. This is there. But if I use this equation, because u is a, according to homogeneity of time, u is independent of time. So because of this equation number 1, this part will be equal to 0. So if it is 0, that means what? this du upon dt is equal to this one. So therefore, what should I write down? I can write down that du upon dt is equal to curly u over curly x1. Oh, sorry, this dt is also here and dt is also here, that I missed. So it is dx1 over dt plus curly u over curly x2 dx2 over dt. As we know that negative of the potential gradient is basically the force, as I discussed in the earlier lectures. So because of that, this term is basically f12, and this is also f of 21 with the negative sign. We have discussed this thing in the earlier lectures, because force is the negative of potential gradient. F is equal to minus du upon dx. So because of that, I should write down it in this way. So therefore, du upon dt, it can be written as minus f12 dx1 up over dt plus minus f of 21 into dx2 over dt. Right? So this is it. So, but force is what? Force is mass into acceleration. So say m1 is the mass of the first particle and m2 is the mass of the second particle, then it is known as m1a1, and a1 is the acceleration of first particle, because force is nothing but it is the mass into acceleration. So if I use this here, similarly it is m2a2 and it is dx2 over dt. But as we know that acceleration is equal to dv over dt, the rate of change of velocity is basically this one. So therefore, I should write down it as a du upon dt is equal to minus m1 dv1 over dt, and dx1 over dt is basically v1, velocity. It is velocity of the second particle. So I can write down it as a minus m into v1, and here it is m2 dv2 over dt, and here it is simply v2. As we know that if we are having a term like this and d upon dt of v square, then it can be written as 2v dv over dt. And if I try to look at this part, it looks like this, because if I put 2 here, 2b and 2, if I multiply it by 2 and divide it by 2, keeping this in mind, so, or we can say that similarly, if I am having half mb square, if I take its derivative, then its derivative can be written as m by 2 2b dv over dt. It can be written like this, right? So therefore, what should I do? Let me arrange it in this way. So what I am doing, I am just writing it as a m1 by 2 and d upon dt of v1 square. Similarly, it can be written as m2 upon 2 and d upon dt of v2 square. It can be written in this way. So du upon dt is here, du upon dt is here, and if I bring this from here to here, because it is a constant, it can be either taken outside the derivative or inside the derivative. So it can be written as minus d upon dt half m1 v1 square. Similarly, it can be written as d upon dt half m2 v2 square. Right? So let us bring these towards here. So therefore, I can write down as a d upon dt plus d upon dt half m1 v1 square plus d upon dt half m2 v2 square and it is equal to 0. So this is a way that how this can be written, that d upon dt, it is half m1 v1 square plus half 2m2 v2 square plus u, and it is equal to 0. So derivative of something, if it is equal to 0, so what does that mean? It is possible if and only if this term is a constant. So this concludes that half m1 v1 square plus half m2 v2 square plus u is equal to 0. This is the kinetic energy of the system, and this is the potential energy of the system. So T plus u is nothing but the E, and it is equal to, sorry, it is constant, and it comes out to be constant. Thus curly u by curly t comes out to be 0. It is a consequence of what? It is a consequence of homogeneity of time. Homogeneity of time, and because of this leads to that the total energy of the system remains conserved. Thus homogeneity of time leads to law of conservation of energy. Right? So that's all for this lecture.